Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. We now discuss the solution of a problem from the section Algebra. This problem is from ring theory, and the problem is related to the concepts and results related to Boolean ring. This question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 704165. This question is suitable for all these examinations. Right. The given question is, let R be a non-zero ring with unity such that R square is equal to R for all R belongs to R. That means each element of this ring R is idempotent. Which of the following statements are true? We are given four options. Option 1, R is never an integral domain. Option 2, R is equal to minus R for all R belongs to R. Option 3, every non-zero prime ideal of R is maximal. Option 4, R must be a commutative ring. Let's now discuss the solution of the problem in detail. We are given a non-zero ring R with unity, and R square is equal to R for all R belongs to R. That means each element of the ring R is an idempotent element. If each element of a ring R is an idempotent element, then such a ring is called a Boolean ring. Now let's call on option 1. R is never an integral domain. R can be an integral domain in a particular case. What is that case? Let R is equal to Z2, that is integers modulo 2 under addition modulo 2 and multiplication modulo 2. It is a non-zero ring with unity, and in this every element is an idempotent element. You can see it. 0 square is 0, 1 square is 1. These are the only two elements in Z2. So x square is equal to x for all x belongs to R. So this has the property of the Boolean ring. The property of the Boolean ring is in it. Right. Now Z2, where 2 is a prime, therefore Z2 under addition modulo 2 and multiplication modulo 2 is a field. And every field is an integral domain. So this is an integral domain having these properties. So clearly it is a field and hence an integral domain. Therefore R can be an integral domain in this case. Therefore option 1 is not true. We go to the option 2. R is equal to minus R for all R belongs to R. Now we see for all R belongs to R, we have R plus R belongs to R because it is closed under addition. When it belongs to the R and it is an element, and every element is an idempotent element, this will imply R plus R whole square is equal to R plus R. This can be written as using the distributivity R plus R multiplied by R plus R is equal to R multiplied by R plus R multiplied by R plus R using the distributive law. Right. Now R multiplied by R plus R is R square plus R square plus R square plus R square is equal to R plus R. And R square is equal to plus R is equal to R for all R belongs to R. Therefore, it is R plus R plus R plus R is equal to R plus R. By cancellation, we'll get R plus R is equal to 0 for all R belongs to R. This implies R is equal to the additive identity of R, that is minus R, for all R belongs to R. Thus, the option 2 is true. Right. Right. We continue in the next slide. We call on option 4. R must be a commutative ring. Yes. Yes. Every Boolean ring is commutative. This is a very standard result what we learn at in our degree classes while studying the ring theory. Right. This is true. Okay, we'll prove. For all xy belongs to R, we have x plus y belongs to R. And because it is a Boolean ring, every element is idempotent. X plus y whole square is equal to x plus y. So use the distributivity and multiply. You will get x square plus xy plus yx plus y square is equal to x plus y. X square is x, y square is y. Substitute. And by cancellations, right and left cancellations using, you will get xy plus yx is equal to 0. And this will imply xy is equal to minus yx for all xy belongs to R. Just now we have seen minus R is equal to minus R for all R belongs to R. Therefore, minus yx is plus yx. So, xy is equal to yx for all xy belongs to R because R is equal to minus R for all R belongs to R. So, xy is equal to yx for all xy belongs to R. That means every pair of elements commute. Therefore, it is a commutative ring. So, R is a commutative ring. Thus, option 4 is true. We move to the next option in the next slide. Yeah, we are given a ring R, non-zero ring R, and with a property, every element is an idempotent element, is a Boolean ring, and every Boolean ring is commutative, and in the hypothesis it is given unity. Therefore, R is a commutative ring with unity. We have this one. Option 3. Every non-zero prime ideal of R is maximal. Yes, this is true. So let P be any non-zero prime ideal of R. We want to prove that P is a maximal ideal of R. We consider the quotient ring R by P. Right. Now the property of idempotency, that is every element is idempotent, is inherited even to R by P. So, right, first of all, let us say P is an ideal, R by P. So, R by P is an integral domain. Why? Because if A is an ideal, then R by A is an ideal, is an integral domain if and only if A is a prime ideal. So we consider R by P where P is a prime ideal. Therefore, R by P will be an integral domain. Why? Because P is a prime ideal of R using this. Right. Now we claim that every element of R by P is idempotent. For this, let us take R plus P whole square, that is R plus P into R plus P. Now recall the multiplication of two additive left cosets. R plus P into R plus P is R square plus P. But we know R square is equal to R for all R. So it will be R plus P. So every element of R by P is idempotent. Let us take an element X belongs to R by P. Yes, I am not writing as R plus P for X. So we take X belongs to R by P. We mean X is an additive left coset of P. And we have just now seen every element of R by P is idempotent. This will imply X square is equal to X. This implies X square minus X is equal to 0. This implies X into X minus 1 is equal to 0. This implies X is equal to 0 or X is equal to 1. Why? We are playing the game in R by P. What is R by P? Is an integral domain. What is an integral domain? It is a ring without zero divisors. Without zero divisors. Therefore, X into X minus 1 is equal to 0 will imply, since there are no zero divisors, either X is 0 or X is equal to 1. So if you take any X belongs to R by P, then you have proved X is either 0 or X is equal to 1. That means R by P has just two elements only, either 0 or 1. So every element of R by P is either 0 or 1. That means how many elements will be there in R by P? 2. The number of elements present in R by P is 2. What is R by P? Is an integral domain. R by P is a finite integral domain. And we know that every finite integral domain is a field. R by P is a finite integral domain. This implies R by P is a field because every finite integral domain is a field. And you recall the result. R by A is a field if and only if A is a maximal ideal. Now R by P is a field. This will imply P is a maximal ideal. Thus, every non-zero prime ideal of R is maximal. Thus, option 3 is true. Summarizing all the options, the answer to this question is options 2, 3 and 4. That is the detailed discussion of the solution of this problem. And this is a very familiar question. A Boolean ring and its properties are very familiar, except that every non-zero prime ideal of R is maximal except this, but all the others what we do in a class. So I say it's a very simple and straightforward question. I am sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure that we are going to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.